x square by 2 factorial.
So like e power h minus 1 will just leave you with h by 1 factorial, h square by 2 factorial, h cube by 3 factorial, h bar 4 by 4 factorial, so on. And what is this getting divided by? It is getting divided by h. So if you divide that by h, what will happen? So all the h terms will get reduced by 1 power. H by 1 factorial become 1 by 1 factorial. H square by 2 factorial become h by 2 factorial. And what will happen to this? H square by 3 factorial. So on. Now what I'm saying in this, I'm saying limit h tends to 0. When I say limit h tends to 0 on this, whenever you put h is a very small insignificant number like 0, all these terms will get removed, right? Meaning they'll be very insignificantly close to 0. You can just remove them. So that means I'm left out with 1 by 1 factorial itself. So you can just replace this information as 1 itself. So we get e power x into 1 e power x. Clear now? So this is why we say differentiation of e power x is e power x itself. Now you asked about chain rule, Ishakan. So suppose imagine someone is asking me how to differentiate e power ax. Okay. But this e power ax looks little different to e power x. So two ways of seeing this. People some way call this as chain rule, or else what I can do is I can just think about applying a property. Property as such exponent rule, if I apply, I can rewrite this as e power a into e power x. Am I right? But e power a has got nothing to do with the differentiation with respect to x because there is no x term in it. You can bring it out. E power a multiplied by differentiation of e power x. Okay. So just
E
now I
power
did.
a, the whole power x, right, sir?
So I was like, what I was doing. Can you see? So e power a x, right? Sorry. So I was trying to bring here e power a the whole power x. Sorry, e power a the whole power x. Now the problem comes here. How would I try to differentiate it? Okay. So either I should think of power rule or chain rule. So I will tell you what chain rule here is. Instead of this confusing ax thing, people tend to write it as ax being t, a new variable. A new good looking, simple looking variable. So when they write it like this, what will happen? That means my y, which was initially a function of x alone, which was e power ax alone, now if you rewrite it as ax as t, now y will become function of, y is still function of t only, but you brought in an in-between variable. No, what is the in-between variable? What is the in-between variable that you had brought? You had brought t as an in-between variable, but I know t is related to x, isn't it? Yes or no? Y is made of
Yes.
e power t then, but t is made of x. So that's why we call this as a chain. So now if I want to find dy by dx, so I understand y is now not directly related to x, it's only related to d, t is only related to x. So then they call the chain to be dy by dt first. Y is relationship with respect to t, and then followed by t's relationship with respect to x. Do you understand this right up?
Yes, sir.
Y is now going to obey what t says, and t is going to obey what x says. So now you see, since I have rewritten ax as t, so y is now just e power t. Now if I want dy by dx, it's going to be dy by dt into dt by dx. So dy by dt, if you do, if I differentiate e power t, I'll just get e power t back into dt by dx. So as I said, t equal to ax. So dt by dx is going to be equal to a, just a multiplier. A differentiation of x will become 1. 1x power 0, that's just 1. So a into 1 a. So what we have got? We have got a times e power t, and finally you need to replace the introduced variable. My introduced variable is t. T is ax to me. So answer is a times e power ax. So did you understand this is nothing but what they call it as chain rule?
Yes, sir.
Yes, sir.
In most of the cases, they will not write all the steps. Okay, even in CBSE, they try to directly write if they see e power ax differentiation, they'll write a e power ax. That's all. They will not be like, expanding this, showing all this chain and all this availability. Understood, Vishaka?
Yes, sir. Sir, also there are properties like differentiation of log x equal to 1 by x and those things. Right? So,
That
like,
that
how do
one
we
also.
apply it in chain rule?
So what do you want to do with respect to differentiation of log of 1 plus x? Log x directly is like a simple function, correct? So suppose someone is giving me a function like log of x square, man. Like someone is giving me a function like log of x square. So here you told me differentiation of log x is just 1 by x. So this also you can prove by the help of limits first principle. So here if I want to differentiate, I understand this log of x square doesn't look like the normal one. So either because we learned logarithm, we can rewrite this log of x square as 2 times log x and then do the differentiation to directly write it as 2 times 1 by x, correct? Or else if you still love doing chain rule, so what you can do is you can let x square be equal to t. So like what I said is like previous time, dy by dt into dt by dx will apply now. After I apply x square equal to t, my function f of x is just which is y, just now will become log t alone, correct? No. So what will be differentiation of log t? 1 by t, right? Multiplied by dt by dx. So if t is x square, what is dt by dx? 2x, right? Because x bar and differentiation will come as n times x bar n minus 1. So 2x. So 2x by t is there, but what I have assumed for t? What is by
X
t?
square.
X square.
Bar. So it becomes 2 by x. Wasn't it much direct when I applied the property of logarithmic property over this? And then if I had gone for the differentiation route, f dash of x, and I got 2 times differentiation of log x, which is 1 by x, 2 by x. So it depends. Certain cases you won't know rules. If you don't know rules, you will take all these chain ideas and all. So chain rule is basically helpful for the kids who learn calculus for the first time because initially they will have little difficulty. So slowly, when they get to understand this is how it works, they will avoid doing this chain. They'll directly write it. How I would ask you to remember this is, if I see log of x square, I will first differentiate it like log. When I see log, differentiation is like 1 by whatever input is given for log, multiplied by differentiation of that, whatever is inside. So 1 by whatever is given to log, x square is given. So 1 by x square multiplied by differentiation of this x square alone, which is 2x. So 1 by x square multiplied by 2x will give you 2 by x. Am I right?
Yes, sir.
Anyone saying something? Lily, how are you? Summation Shan, I shall live.
Yes, sir, I'm fine.
Dul,
Good, sir.
what happened to your throat?
I haven't spoken to anybody since the morning, like to my parents, so I guess.
That created change in voice. Okay.
No, so also because I have to take my face test today because it's the last day. Have been postponing it since leave started, so I have, yeah,
Sir, will you be coming
contemplating.
back, sir?
Yeah, Summation Shan.
Sir, no, will you be coming back?
I'm not sure, Summation Shan. Like, I cannot promise that yet.
Okay.
Right? So I shall have changed the name. Long live
Yes,
Sir,
Ashal.
sir.
now,
Formal name.
Yeah.
Formal name, yeah.
Yes. Great. Okay. So Vishagan, I guess you are now clear with this thing. And did you see the product rule video? I guess you would have
yeah,
understood
sir.
how it works. So
Yeah,
it's not
I
about,
understood product.
yeah, there's no limitation on product rule, just about between two things. There can be n number of functions getting multiplied. Suppose I'm going to give you like log x into x square into sine x as a function. I'm going to ask you about differentiation of this. Then you will understand there are three functions as such. U, v, and w. There are three functions. So differentiation of the three functions as such, like in product rule, you would have seen I said like you keep one function undisturbed and differentiate the other, like that pairwise you do. Now there are three things. So when there are three things, what you do is you leave two things undisturbed at a time and differentiate the one thing. So I would say uv dash uv dash w plus u dash vw. Clear? So meaning you are allowed to differentiate only one thing at a time. So the result will be log x times x square, differentiation of sin x, cos x, log x, differentiation of x square, 2x, and sin x as it is. U dash, differentiation of log x is 1 by x square times and sin x. Clear? So this will be the differentiation of the product here. If you take three things being in multiplication. Clear about the product rule? Anika, you have joined us, Anoka?
Sir, autocorrect does not like my name.
Okay.
So that shall be her new name from now on.
Okay, that's if you like. Okay.
Sir, how
For the
does
second-
differentiation work on different functions?
How does differentiation work on different functions? Okay, it's been a mystery forever when the power is a variable. Good. Okay, yes, Vishaka, two questions now. So first question, I'll answer that. So when power is in the variable place, what should we do? So suppose my function is like say a power x, and I want to
Then
differentiate this.
it should be,
Uh,
if we differentiate this term, it will be x times a power x minus 1.
that is wrong because
That's
the base is not your variable. The power is your variable. Okay, you're not allowed to differentiate it by the rule of x bar n. X bar n, you know, differentiation is going to give you n times x bar n minus 1. Here, this rule applies because x was your base. N was not the variable. X was the variable. Okay. But here, x, which is your variable, is there in the power place. So when you want to differentiate these kind of things, we need to first pull the power down. So that you know that beauty will happen if you apply log. So I'll apply log on this equation. So I'll get log y equal to log of a power x. Then by the logarithmic rule, the power will come down. So it will become x times log a. Log y equal to x times log a. Then you can differentiate with respect to x. Differentiating y with respect to x. So log y, just now we know log is differentiation 1 by y. 1 by y will come. So since you are differentiating y with respect to x, along with this I write dy by dx equal to x times log a. Log a is just a constant. Differentiation of x is going to become 1. So 1x bar 0. So what happens here? So dy by dx is equal to y times log a. And what is my y? Y is equal to a par x. So my answer for this is a par x log a. And it is not x times a par x minus 1. It is a par x log a. Is that clear? So whenever you see power in the variable, variable in the power place, your first thing that you got to do is pull them down with the help of log. Then you differentiate. Yes, Vishaka, what is the other question? How does differentiation work on different functions? So like basically, as I have explained to you, what is differentiation? Differentiation is basically trying to give us, how will the, see if I draw a line, okay? If I just draw a line, I don't need a differentiation as such for this because a line will have a fixed angle with the x-axis. Am I right? If a line has a fixed angle with the positive direction of x-axis, that means its slope is also fixed, right? M equal to tan theta. You have learned in coordinate geometry chapter last year, 10th standard. But if it's not a line, if it is not a line, and if it is a curve as such, then for every point, like say you can assume drawing a tangent to every point, and all these tangent lines are tending to create different angles with respect to your x-axis, correct? So that means the slope of each of this tangent line is changing. So if the slope is continuously changing, okay, so that is what we are saying rate of change of that function, correct? Because my function continues to change. So here your slope isn't fixed. At every point you are going to get some different slope. Okay, at every point in the track of the curves movement, you are going to keep getting different curves. I mean different slope values. So I showed you in the video about like why it was for sin x graph, why the differentiation was called cos x. Because at every point when I keep drawing tangents to every point on sin x graph, and if I keep noting the slope values by the angle it made with the x-axis, and I plotted those values as like with respect to x-axis, if I'm plotting dy by dx value, then I got a graph like this, which is exactly the replica of cos x graph. That's why I said differentiation of sin x is cos x. Like this, they will be doing for every graph. Okay. So log x, just now you said no, log x differentiation is 1 by x, you said. That means for log x graph, if I start drawing tangents and I start noting the slope value made by each of those tangents and plot a graph of x dy by dx versus x, then I'll be getting the graph of 1 by x. Did you understand what I'm saying?
Yes, sir.
Good. So I'm going to show that in the graphical way also. It will be useful, suppose. See, but tell you one thing, but like there are two approaches. One thing is like if you keep running again, just solving the problems, at one stage you will lose the ability to solve problems quick. And only if you have familiarity of the question, you'll be able to solve it faster. But if you're able to understand the subject as well, then things will become much more easier. So are you able to see the screen?
Yes, sir.
Yes, sir.
Now this is my log x graph, okay? So in log x graph, like every point I'll be able to draw a tangent because it's a curve. And you can notice the angle like that's tangent is going to make with the curve, and you can start making the slope with respect to that. So like as I said, for example, you notice this point. What is this point? Can you see? 1.867 comma 0.27114. So I'll even mark it so that we can do some calculation. I'll just put x equal to 1.867. Okay. Follow this closely. And also take a very close point, 1.868. So you are not able to see them because I have taken them very close. So what I'll do is I'll just note down the values. For 1.867, what is the value, people? 0. What y value we achieved? 0.27.
0.271.
W1.
Okay. So now let me also take that x equal to 1.868. So what value we are achieving?
0.271.
Y was coming to be, sorry, did you note it down?
Sir, 0.27.
1377, right?
Yes, sir.
0.27 1377. Okay, if the meeting ends, also rejoin through the same ID. So this is the value that we are achieving for y equal to x equal to 1.868, and this is the value you are achieving for x equal to 1.867. Understood, everyone? Now shall I try to get to the slope here? So as I said, slope, it's basically change in the y values. So change in y values, the new value that you got is 0.271377, and the old value was 0.27114, correct now? Yes. And the new input is 1.868 minus the old input is 1.867. So this is what basically our idea of slope is. At very close inputs, the change in the outputs. So now I am going to calculate this, people. Let me see when I calculate what happens. So 0.271377 minus 0.271144. So that is kind of giving me 0.000233 divided by this 1.868 minus 1.867. So that's going to give me 0.001. Okay. So when I divide this 0.000233 divided by 0.001, I'm getting an answer like 0.233. Is that clear?
Yes, sir.
So that means almost at proximity of this numbers 1.867 or 1.868, which is almost like when they become like almost a single point, then the slope value at that point is going to become like 0.233. Now we already wrote what is the differentiation of log x. Now I'll show you the 1 by x graph. I'm showing you the 1 by x graph. And let's also I'll remove these numbers for calculation part. So for this 1 by x graph, let's figure out what is at that value at that same place. Zoomed in so much, I guess. Okay, and I also have to make sure whether it was okay 1.868, right? Okay, did this check it as log x or ln x? That also I didn't check. Okay, because differentiation of log x base c is only 1 by x. Okay, if it was any other base, we need to do base changing rule and do it. So let me confirm it once. Let me write ln x value and check whether I get the same. Or else we have to redo this calculation. Okay, I know I would have taken your time, but still, let's redo this calculation a bit. So I will confirm again for the same values so that it'll be better for a calculation. 867 at x equal to 1.867. What is the value? Okay, see, it's different. The previous thing that Desmos had given was base 10, I guess. So at x equal to 1.867, the y value that we are achieving is 0.62433. 0.62433. Okay, let me also take the very immediate value 1.868. Let me see what value it's going to give me for 1.868. It's giving me 0.62487. It's giving me 0.62487. Okay, so let's see the change that's happening. So the denominator is still the same because I kept the same difference in the inputs. Now let's look at the outputs. The new output is 0.62487 and the old one was 0.62433. Okay, so let's calculate this. The numerator alone is going to change. So let's see what happens. 0.62487 minus 0.624 0.624
0.00054 difference.
one second, sorry. Yeah, correct. What you said is right. So that's me getting 0.00054. Correct down. So this 0.00054 when it is divided by 0.001, we are getting around 0.54. Am I right? So now, as I said, the differentiation of log x graph is nothing but 1 by x. Now let's go and check at almost this 1.867 point or 1.868, almost there. What is the value? Can you see? I'll remove the ln x graph also. Can you see, people, what value we are getting?
Approximately 0.3.
Approximately 0.54, right? So because I was showing 867, so even if you take 868, I was showing, see 867. So that means they are rounding off to the third decimal, so which means 0.54. That's what I was saying. So basically, we are finding the change in the y values with respect to the change in x values, and we are starting to plot it as dy by dx versus x. Okay. And that's how we are getting this. So this is no magic. Like we're just plotting it. Someone had already done it. So that's why they claimed, okay, it's nothing but a 1 by x graph. And also we have the limits first principle, which helps us to also prove the same, correct? Did you all understand
Yes, sir.
how this had worked?
Yes.
Sir.
Great.
Sir,
So
also like
yeah, Vishal.
I have another problem. Like when I was randomly messing up with Desmos, there were like discontinuous lines for certain equations. So how do we assume the limits for those?
See, there are so many disruptions that could happen when curves become discontinuous. Okay. So like limits as such need not be defined at certain points. Now, again, the limits is a bigger word to use. Because limits as such like very close to a point and in neighborhoods, what value it is assuming, what value it is showing. That is what is basically limits. If it is agreeable, then we say the function is like having a limit at that point or else not. For example, if you see tan x graph, okay, shall I show tan x graph? If I show tan x graph,
Yes, sir.
you all know when you go towards like that pi by 2 value, uh, right? What is tan of pi by 2? Tan 90 degree.
One, I
And
mean,
90
sorry,
not defined, no.
sorry, not different.
It's like going towards infinity. So I will say as a tan x graphs idea, in tan x graph idea, when I go, my angle is getting close to 90 degree and it goes close to 90 degree, my value of tan x is also approaching infinity, correct? Like close to 90 degree from left side. But that means if I cross 90 degree a bit, even by a small bit, my tan x would have been fallen down to minus infinity. Understood how? You have seen your tan x graph, it's periodic. It keeps creating the same thing again and again. Correct? No.
Yes.
So you can see that here. I'll show you. So can you see the tan x graph? This is the tan x graph. We know every trigonometric function is periodic. At extending to 90 degree, 90 degree, if I write in radians, it is nothing but pi by 2. Pi by 2 means 3.14 divided by 2. So 1.57. Close to 1.57, you can notice the value of the tan x graph is getting very close, asymptotically closer to that line of 1.57, but it will never touch. We'll say it'll touch at infinity, it will never touch. So, but then suddenly after that pi by 2 value, you see where tan is jumping to. This side, right side of that 1.57, you can see tan x was jumping towards negative infinity. So such a kind of curve, we term it as like jump discontinuous curve. So here someone, if they are going to ask me what is tan tending to, what limit extending to pi by 2, if someone is asking me what is limit extending to pi by 2 tan x, then I'll say the limit doesn't exist. I'll have to say the limit doesn't exist. Why? Because left side of, we'll say left hand limit LHL and right hand limit RHL. That means LHL means the value that you're taking is little less than pi by 2. Pi by 2 minus means little less than pi by 2. And here it is pi by 2 plus, meaning little right of pi by 2. So in that case, this was tan x graph was going towards infinity. And here a little right of pi by 2 value, tan x graph was going towards negative infinity. So they are not tending towards or they are not going towards the same number, right? So that's why we will say the tan x limit is not defined at pi by 2 or those points where it is having that jump discontinuity. But at any other point apart from those pi by 2 or its repetition in periodicity property, they will be defined only. Limit will give you almost the same number either side, left side or right side of that number. Limit will give you the same thing only. Any other doubt?
So can we do sine 1 by x?
Sine of 1 by x. You know about the best part of sine x graph, sine graph. Sine is a kind of a limited graph, meaning it will always be range bounded between -1 to +1. But the problem with this 1 by x thing is, when you get very close to 0, when x gets very close to 0, this 1 by x is also going to be like towards infinity or minus infinity and all. So at those places, for example, if I take x equal to 1, so I'll get sine 1. Sine 1 is like 1 is like in a radian. You should consider as radian. As a radian, it's like little less than pi by 2. Okay. So that means it will have some finite value, but not equal to 1, but less than 1. So that range boundingness will be there, just like a sin x graph. But when it comes closer to the 0 part, you cannot actually say the numerical value, but you can be sure that it is going to be like only between -1 to +1. So then on that zone alone, you will see bigger oscillation disturbance. Why? Because when it came close to 0, that means the value here is tending to infinity. Though you tend to infinity or minus infinity, sign is going to only obey the idea of -1 to +1. But you cannot take a new exact numerical value like whether it's -1 or whether it's +1 like that. So in that zone alone, like you will see a lot of disturbance. So that is called oscillatoriness. So in physics, you'll be learning it. So you'll be seeing how that oscillatory disturbance is happening when you are not able to plot certain values. So this is your sin x graph. It's a very obedient graph. It keeps moving properly up and down, very much regular to school, regular to class kind of graph it is. But suddenly when sin 1 by x happens, when life takes upside down, so you see what's happening. Very close to 0, it was like vigorously moving, but you cannot take exact numerical values at all. Even if you zoom it, you will understand still close to that. You will feel like it's only like some shaded thing because they are telling you indirectly you cannot take some direct numerical values as such. Okay. And I would love playing with the graphs, and I'll also suggest the same thing to you. Like to play with the graph always. So see, sin x is a graph, trigonometric graph, periodic graph. How beautiful it is. And like line, y equal to x is a graph. It's a linear thing. Okay, but what would happen when both of these get multiplied? You see what is happening? Close to the 0 zone, it will be small looking curve, just like sin x. But after that, it will become bigger and bigger and bigger. So many tough or time consuming questions as such, right, will just rely on one simple thing. And one simple thing being like whether you are able to visually connect to those things or not. Do you understand what I was saying?
Yes, sir. Like the
Yes.
line acts as the
So now one more
intersection
thing
points
is,
of.
yes, correct, Vishakan. One more thing is beautifully, this y equal to x is a continuous graph. It's a polynomial and every polynomial will be continuous. And sin x is also a continuous graph, correct? Then by the idea of continuity, when you add two continuous graphs, it will still be continuous. Can you see the beauty? How y x plus sin x looks like? It looks like a curvy staircase, right? Suppose once you become an engineer, you want to apply something new, you can do such things in your life. X plus sin x like a curvy, like staircase thing. So when you add two continuous functions, right, it will also be continuous functionally. Even if you subtract them, you're still going to be continuous. When you multiply them, it's still going to be continuous. But when you divide them, it's not necessary. Why? Because when you divide them, the denominator should not be 0. So now you see I'm dividing x by sin x. You know the difficulty. Why? Because whenever your denominator is going to be 0, it's going to become discontinuous. So but sin x will become 0 at all the integer multiples of pi, right? At 0, at pi, 2 pi, 3 pi, 4 pi and all, sin is going to be 0. So you cannot have a numerical value for x by sin x at those points. Clear on what I was saying? But see how beautifully the graph is. Okay, did you all understand?
Yes, sir.
Yes, sir.
Yes.
So simply these kind of questions are making, what they'll do is they'll take two functions, but at the same time, if you take one continuous function, one discontinuous function. Okay, so we have a lot of examples to quote for continuous functions. Let's also think about some discontinuous functions. Okay, what shall I take as discontinuous? I won't take polynomials. I won't take trigonometric because I know even if I take trigonometric, yes, I can go for like tan x, secant x, and all, right? Because they are not they are also discontinuous at certain points, right? So as I just gave you the same example, I will reduce it down to x and tan x example. X is continuous, but tan x is, what about tan x? Tan x is discontinuous, right?
Discontinuous.
Yes, sir.
Discontinuous whenever like the angle multiples go in form of pi by 2 forms, odd multiples of pi by 2, it becomes discontinuous. So what would happen if I add a continuous graph to a discontinuous graph?
Discontinuous, sir.
It will be discontinuous at those points. X plus tan x. You see now what happens. When I do x plus tan x, it would still be discontinuous at those points where tan x was not defined. Same thing will happen when I do x minus tan x. It still be discontinuous at those points where tan x was not defined. But when you do x into tan x, like tan x don't be defined at that point. So like still it's infinity form, which is like not allowing it to grow. I mean, still discontinuity is happening. The x by tan x. So like whenever you learn things or properties, I would suggest you to go with the visual approach because visual approach will stay in your mind forever. Understood now what I'm saying?
Yes, sir.
Yes, sir.
This is about one continuous and one discontinuous graph making up. But sometimes two discontinuous graphs when you take, so they might sometimes lead to continuous graphs. Like say I take tan x into secant x. Okay, suppose I'm taking tan x into secant x. Sometimes, not every time, but sometimes they might lead to continuous graphs. So those kind of examples only you should be aware of seeing how you can make it continuous because the question making, it's not about theoretical alone. They will expect you to check how you can make discontinuous graph continuous. What changes can you do so that they become continuous? It's a very beautiful topic, but like as I'm saying, though they are being introduced in NCERT level in basic calculus as such, when they start this topic, they will just quickly say the formulas that you need to remember, and they just give you some questions on product rule, quotient rule, and all that. They won't get much detailing onto this, but once they start this LCD limit continuity differentiability, they will start giving you questions on this. But your brain needs some processing time and how things work. But for that, that's why I'm saying we can feed these seeds into our mind and let mind do the remaining work. Okay, understood, right? What I'm saying.
Yes.
So, for example, the same thing tan x, which I was saying here, like tan x, though it is discontinuous, where it was discontinuous only at pi by 2 things, pi by 2 or odd multiples of pi by 2 forms. So then, if you are giving or multiplying it by some function where at odd multiples of pi by 2 it will be 0, then such function will make it continuous. Huh? Are you able to understand my question?
No, sir.
Like though the number tends to infinity here, but if you are going to multiply it by some number 0, then it will still drag it down, no, to 0,
Yes.
making it continuous. So that's how we play with this discontinuity and continuity. Is that clear? Okay. So forthcoming, like I will continue to put some nice, interesting graphical forms on continuity, differentiability, and all. But like take them as seeds for your thought, food for thought, we'll say. more your mind is gonna keep itself interested towards the application part. The optimization idea was exactly that. The optimization video which I had put like was exactly a complete applicative property. Like Aisha kind of promoted me on that thought process of where to see math in real life. So that was a very cute application of math in real life. Like not just Aisha, like everyone will have that question in their mind, like where to use, how they are using. But I was saying just adjusting in carpenter being in use, but not necessarily just be a carpenter. You just imagine nowadays many people are doing rooftop gardening and all that, and they're just meaning just doing farming in their free time, and they're just exporting goods, all that. So with the available space, how you can deal with things. So that could be a real life application for anyone, right? Or you have a small space, you want to have a reading room in that, a library in that. So like how to construct. So all this you can bring into your real life. Real life is really beautiful with math in it. Okay.
So can you like tell us about differentiability, sir?
Louder, Mish.
And differentiability, sir. Like what does it mean, sir?
Differentiability. Good question. Mish had asked. So differentiability is about able to draw tangents. Okay. Differentiability is all about able to draw tangents, Mish. So like this 1 by x graph, if I'm able to take, will I be able to draw tangents at x equal to 0? If a function itself is not defined at a point, will you be able to draw tangent at that? That's not possible, right? Suppose I take mod x graph. If you take a mod x graph will come like this, because right side of 0, it's it will just break into x itself, because x is non-negative means there's no role that modulus got to do. But if x is negative, then it will break down to minus x. So this side the graph is y equal to x, and this side the graph is y equal to plus x. Now check at this. This y equal to x graph image is having an angle of 45 degree with the x-axis. That means its slope is 1. But this y equal to minus x graph, if you see, it is having a slope of, if it's having an angle of 135 degrees. It's an angle of 135 degree. That means its slope is minus 1. So that means it might have the slopes at these points, but at this point 0. Left. So just like in limits, we see left hand limit, right hand limit. In differentiability, we look at left hand differentiability, right hand differentiability. LHD and RHD we say. So right side of 0, you have differentiability, differentiation slope value to be 1. Left side of 0, I see the slope value to be minus 1. So there is an abrupt change from minus 1 to plus 1, no, at this point of 0. So then we would say that this function is not differentiable at this point. Understood now?
So like where on any function where it's discontinuous, we can tell it's not differentiable also.
Of course, at those points, it won't be differentiable because there are rules for differentiability. First thing, the function has to be defined at that point. And if the function is defined at that point, then the limit, left-hand limit, right-hand limit should be same. But in this case, I have y equal to mod x graph. The left-hand limit and right-hand limit are almost same. Meaning 0 plus if I substitute to mod x, it's still going to give me 0. And 0 minus if I'm going to substitute for mod x, it's still going to give me 0 form, right? So that means it is limit is there, function is defined, but look at the differentiability. The derivative right side of 0 and derivative left side of 0 are not same, no.
Yes.
They are making an abrupt change from minus 1 to plus 1. So in that case, we will say it's not differentiable at those points. At abrupt changing points of curve's nature, it is not differentiable. So then I might give you a much simpler example as y equal to x square. Suppose I'm taking the graph of y equal to x square. So now you might think, sir, is this point abruptly changing or not? See, this curve was not changing its definition, no. Right side of 0 or left side of 0, y equal to x square is y equal to x square only. So right side of 0, RHD if you take, x tends to 0 plus, still it is x square graph only. Left side of 0, when you go for 0 minus, still it's x square graph only. When you differentiate x square, what will you get? You'll get 2x. When you differentiate x square, you still get 2x. You substitute x tends to 0 minus or x tends to 0 plus, your answer is going to come like 0 minus or 0 plus only, no, meaning very close to 0 both. So that means I would not consider this as an abrupt change. I would still say the graph is differentiable at 0. Understood?
Yes, sir.
So you tell me the differentiation of x square. X square differentiates 2x. So that means if you draw the graph of 2x, you see little close to 0, very close to 0. What value you are getting? Very close to 0. What value you are getting?
Yes.
0.00 something, correct? Little left side of 0 also, what value you are getting?
Same, like similar.
They are tending to the same number, no? The
Limits
derivative
approaching.
is tending to the same number. That's why we say the derivative exists there. And yes, I can say at this point 0, I'm able to draw the tangent line. The x-axis itself is the tangent line, no?
Yes, sir.
Understood how?
Yes, sir.
Good. So a very good question asked by Imesh on that.
So one more thing, sir. Like,
Yeah.
so what is up with this F double dash, sir? Because like we
It
just
is
know the formula. It's like
correct. You are
differentiating
just seeing it as a formula procedure, Lily. But the point is, F double dash is looking at the rate of change of slope again. Okay. So I said you like first graph is between y versus x. Second graph is between dy by dx versus x. Correct? No. The third graph is change of dy by dx with respect to x. That is only F double dash graph. What happens to the slope? What happens to the slope? Whether the slope is increasing or the slope is decreasing with respect to the previous slope. So for instance, I'm taking y equal to x cube.
Double dash is only applicable for cubic functions. Like for quadratic, it won't even be applicable, right?
It will come to a constant thing.
Yes, sir.
So I have written all three. X cube is the function, 3x square is the first derivative, 6x the second derivative. Now if someone is seeing only the graph of 3x square, okay, and they are able to plot to the change happened between every point. For example, you notice this 1.162, the value is 4.05073. 1.162, you add 4.05073 as the value. So this is the like x value, x being this, and this is the dy by dx value, f dash x value. So now let's take a very close value, 1.163 as well. So at 1.163, you see the value, it is 4.05771. 4.05771. So now there is a change happening in the slope itself, no? So 4.05771 minus 4.05073 divided by 1.163 minus 1.162. This is basically your second derivative at that point. Understood? If you want me to calculate, I'll calculate and tell you. So 4.05
0.00698 and down will be like 0.01.
divided by 0.001. No,
Yes, sir.
it comes
Top
around
will be
6.98.
Yes, sir.
So now
Yes,
close to that point, you can see in the second derivative graph, Simesh. Second derivative graph, see the value you are getting close to that. What are you getting? Did you get this?
yes, sir.
So that's what second derivative. Second derivative is actually going to help us to show whether the slope is increasing or decreasing. But if you know x cube graph is a strictly increasing graph, no?
Yes.
That means slope will be continuously increasing, right?
Yes.
That's why your second derivative has come as like 6x. 6x is a linear line. From left to right, if you see 6x graph, it's continuously increasing only, no?
Yes.
On the other hand, if you are taking a x cube minus 3x square, sorry, minus 6x square plus 11x minus 6. This is also cubic only, but it was not continuously increasing or strictly increasing. From left to right, if I see this graph, it increased till this point, then started decreasing till this point, then after that it's increasing. Correct? No? So if it's not strictly increasing, then its slope will also not be strictly increasing, right? It will increase till a point, then it will fall down, then again it will increase. So like I'm going to show the slope thing for this graph. So that will be 3x square minus 12x plus 11. So as you can notice here, the slope value was decreasing till this point, then it started increasing. Okay. These are the slopes plotted. Now if I see the rate of change of slope, the change in the slope level, so that will be second derivative, 6x minus 12 alone. As such, the slope alone, the slope was continuously like as such, between those small intervals, it was increasing for me because it became linear. Clear now?
Also, like many questions they ask if this function is continuously increasing, this is function is continuously decreasing. Like those questions they ask. So, like, what do you, like, if we differentiate it, like, we'll get a graphical approach, but without the graph, what is like the approach towards?
Yeah, I don't really need the graph. I really need the graph only to understand how things work. But once I start understanding it, or once you have understood it, then directly you can just check whether the graph is a piecewise graph, whether it has different definitions around that point, and then you can take that individual definition, start differentiating, and then substituting the values. That will become very manual. But before it becomes manual, I want you to enjoy the math behind it. If you just skip the good part and just start doing the manual math of procedural math, you won't be able to connect to some very hard concepts or something. Okay. So I understood your question, it means like, but you need to wait till you see such parts on math. Okay, I'll continue to post some more inspiring videos on this. So once you're all seeing through, then the manual part, let that come into picture then. So this itself, even many 12th standard kids who kind of are preparing for this exam or writing the exam, uh, still they won't, many people are not sure of what is second derivative, what it is, how it's happening, how it's working. They just memorize it as a procedure. Okay, if they ask this question, I should do this procedure. If they ask that question, I should do that procedure. So procedurally, you cannot confine math.
Yes, that's what I used to do to know. Like f double dash is f double dash. It's just differentiating two times for me, but it's just now like you just don't know how it works.
So that's why I gave you the idea, right? What you do is like you take certain points and see how the slope value is changing over those points. Whether you see it as a positive change in slope or negative change in slope, based on that, the second derivative graph will be showing some differences. Okay, that I will show you based on the second derivative alone. I will put a video. First derivative separately, and second derivative will put a video. Then once you see that, then I think things will get better.
So for the limits, like first derivative is the like it's like x approaching to zero, limit x approaching zero for that function.
Hmm.
So how will we represent it, the limits form for the second derivatives?
So we do again, okay, if you are interested in like seeing limits, first principle of limits for getting the derivative, then we do the same thing, but we do it on f dash of x plus h. That's all. Because we know the limits first principle. It says dy by dx is given by limit h tends to 0, f of x plus h minus f of x by x plus h minus x, correct? So this is dy by dx. Then d square by dx square is going to be again limit h tending to 0. But now this time it's on f dash of x plus h minus f dash of x by x plus h minus x.
So what?
So fine, people will connect next session soon after seeing some more conceptual videos. Okay. So thank you for coming.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.
Thank you.
It got a bit boring, sir. Like, I mean, like we don't have anything new to do. Like doing the questions and questions. That's why it gets boring.
I know that's what I'm saying. When you enter into the manual mode of doing things, then math would get little, right? Not just math, like, every subject would get boring, like rather than seeing in-depth understanding of it.
In that Khan Academy, I started this one thing, but still, it's not the feel of the classroom. Just the video, finally.
Yes, but hope things will get better, really.
So I added you in my teachers list for Khan Academy. So maybe got a mail someday, like
Got
1 month, 2
me.
months. ago. Yes, I might have got a mail before. Like I added like 6, 7 months ago. I didn't tell you. Just need your Gmail ID, so I entered.
I don't remember getting a mail, or maybe I would have
No,
just deleted
anything I
because
do, like you will get an update. Any course I
you're
start, you'll
using my mail
get
ID
an
everywhere.
Sir, probably it's in spam folder, sir.
I get to know him, yes. Okay, bye, Abhi. Bye, Umesh.
Bye, sir.
Bye.